So if you're a design engineer, you already know the future of computing isn't just about getting smaller or faster, it's about getting colder, a lot colder. To actually control a quantum computer, we need our electronics to work right down near absolute zero. But how in the world do you get a classic silicon chip to talk to a super fragile qubit in that kind of extreme environment? Well, the answer is kind of surprising. It's in the world of cryogenic CMOS, and that's exactly what we're going to break down today.
All right, here's the plan. First, we're going to tackle the main problem. How do you even control a qubit? Then we'll get into the really cool part, the unexpected performance boosts that pop up when you push CMOS to its cryogenic limits, and of course, the hidden problems that come with it. We'll also meet a very special kind of transistor that acts as our quantum translator. And finally, we'll put all the pieces together and see what it takes to build a full quantum interface.
Okay, so here's the fundamental issue. Qubits, right? They're the heart and soul of a quantum computer, but they are incredibly delicate. They only work when they're basically at absolute zero. Now, to control them, we need a classical electronic interface. But running a bunch of long wires out of that super cold cryostat, that introduces way too much noise and heat. It's a non-starter. So the only real solution is to put the controller right there in the cold with them, sitting side by side. What you're looking at here is the entire signal chain we have to build. Over on the left, you've got the qubits. They output a signal that's only about 1 millivolt. I mean, that is barely a whisper above the noise floor. It is way, way too weak for any normal CMOS circuit to even notice. So first, it has to go to an intermediary, a single electron transistor, or SET, which is basically a preamplifier. The SET cranks that signal up to a level that our cryo-CMOS logic, over on the right, can finally read. The big challenge? Making this entire chain work perfectly inside that cryostat.
Now, you might be thinking, wait, you're going to take a standard CMOS chip, one that's designed for room temperature, and just plunge it into liquid helium? That sounds like a recipe for disaster. But it turns out the cold actually unlocks some incredible, almost magical performance enhancements. This isn't just about making it survive, it's about making it better. And this slide, right here, this is the money shot for any circuit designer. It shows the IV curves, the electrical fingerprint, of a MOSFET at room temperature versus a cryogenic 10 Kelvin. And the difference is, they aren't subtle, they're total game changers. So let's break this down piece by piece. Let's zero in on quadrant 1, up in the top left. See that red curve for 10 Kelvin? Look at that slope. That's what we call the subthreshold swing, and it gets incredibly steep. What this means is the transistor turns on and off way more sharply. It's like going from a mushy dimmer switch to a satisfying crisp toggle switch. Now, you'll also notice the threshold voltage, VTH, goes up. That's because the silicon's energy band gap actually gets wider at low temps, and the Fermi level shifts, so you just need a little more voltage to get the device to turn on. And the scale of this improvement is just, well, it's staggering. At room temp, your subthreshold swing is hanging out around 85 millivolts per decade. At 10 Kelvin, it absolutely plummets to just 3. So why do we care? A steeper swing means radically less current leaking out and the transistor is off. And when you have millions of these transistors, that adds up to a massive reduction in power consumption and heat. And those are the two biggest enemies you have inside a cryostat. Okay, now look at quadrant 2 in the top right. This tells us what happens to speed. At room temperature, the silicon crystal lattice is basically vibrating, right? It creates these things called phonons that get in the way and scatter the electrons, slowing them down. But when you cool everything down, those lattice vibrations just die down. The path gets clearer, and with a clearer path, the electrons just zip right through the channel so much faster. For us engineers, this higher carrier mobility means faster transistors, plain and simple. And that means higher speed processing. Of course, it's not all a free lunch. Looking down at quadrant 4, we see that some of our old familiar problems, well, they follow us into the cold. Drain-induced barrier lowering, or DBL, is still very much a thing. This is where a high drain voltage basically tugs on the channel, lowering the energy barrier and causing some unwanted leakage. It's a classic short channel effect that we absolutely have to model carefully to make sure our circuits behave the way we expect them to. And to account for all these effects, our models have to be spot on. It all starts with correctly extracting the threshold voltage. You've got two main ways to do this: the maximum transconductance method, which looks for the steepest part of the curve, and the constant current method, which just finds the voltage you need to hit a very specific current target.
Look, neither is perfect, but choosing the right one and really dialing it in is absolutely crucial for building a model that actually predicts what's going to happen inside that cryostat.
So, we've got a near-perfect switch, we've got faster carriers. What's the catch? Well, the cold creates its own very unique problem. And it has to do with the atoms we intentionally put into the silicon to make transistors work in the first place, the dopants. This is what we call dopant freeze-out. See, at room temperature, all those dopant atoms we add are ionized, creating the free carriers we need for the transistor to work. But when you get extremely cold, they can just stop. They become electrically neutral again. They freeze out. And the real problem is, this doesn't happen uniformly. These charts show the active dopant density across a device. As you watch the temperature drop from 300K down to 77K, you can see these huge, random spikes just pop up out of nowhere. This creates massive, unpredictable differences from one transistor to the next.
And this variability is the key thing to take away here. The dopant peaks get way worse at 77K. You can also see that older planar devices suffer more from this than modern FinFETs do. And for P-type transistors, you even see new variation peaks showing up, probably from germanium leaking out of the source and drain. If you're an engineer trying to build a reliable, large-scale system, these random fluctuations are an absolute nightmare. Okay, so this brings us to a really special device that's absolutely essential for bridging that last mile to the qubit. Because even with our souped-up cryo-CMOS, we still can't directly read that incredibly faint quantum signal. We need to call in a specialist, the single electron transistor. A single electron transistor, or SET, is nothing like a normal MOSFET. It's an ultra-sensitive device that literally operates on quantum principles. It is so sensitive that it can detect the change in charge from a single electron. And that extreme sensitivity is exactly what makes it the perfect sensor for reading the faint energy state of a qubit. So the whole readout process is actually pretty simple, but it's really elegant. First, the qubit gives you its result, that tiny 1 millivolt signal that tells you its final quantum state. Next, the SET detects this tiny change and amplifies the signal by about 30 times, boosting it up to around 30 millivolts. And finally, that amplified signal is now strong enough for our cryo-CMOS logic to reliably see it and say, okay, that's a 1 or that's a 0. So if you want to boil it down to one sentence, the SET is the critical translator. It bridges this massive sensitivity gap between the quantum world, where info is held in the state of a single particle, and the classical world of voltages and currents that our good old CMOS circuits can actually understand. Okay, let's pull it all together now. Let's think like the engineer who actually has to design this quantum interface. What we've got is a set of amazing benefits and one really big challenge that we have to manage. It's a classic engineering trade-off. This table pretty much sums up the engineering balance sheet. So on the plus side, going cryogenic gives us that super low sub-threshold swing, which means way lower power, and enhanced carrier mobility for faster circuits. That's a huge win. On the minus side, our threshold voltage shifts around, so we have to adjust our designs for that. And the big one, we have to deal with the device variability from dopant freeze-out. That is our #1 reliability challenge. But look, these challenges aren't roadblocks. They're the engineering problems that we are actively solving as we speak. The physics is telling us what's possible. By really digging in, understanding, modeling, and designing circuits that can master these cryogenic effects, we can take the most mature manufacturing technology on the entire planet, CMOS, and turn it into the key that finally unlocks large-scale, fault-tolerant quantum computing. So this really brings the classical controller within our grasp. But it just raises the next big question, right? With the control plane more or less solved, what becomes the next major engineering bottleneck on the roadmap? Is it improving qubit coherence? Is it designing scalable error correction? Or is it tackling the immense challenge of just keeping millions of qubits cool? That is the next frontier.